So we're going to be using what we know about how to add and subtract random variables, their means, and their standard deviations on this problem. Okay? So this will be what your homework problems look like tonight. Suppose a used car dealer runs autos through a two-stage process to get them ready to sell. The mechanical checkup costs $50 an hour and takes an average of 90 minutes with a standard deviation of 15. So we're not setting up a probability model. We're given the mean and the standard deviation. The appearance prep, that's where they wash and polish it, costs $6 an hour and takes an average of 60 minutes with a standard deviation of 6 minutes. You guys need to stop talking. Okay. What are the mean and the standard deviation of the total time spent preparing the car? Well, the total time spent preparing the car would be the mechanical checkup plus the appearance prep, right? They got to make it look pretty before they put it out on the lot. So, for number 1, the expected value, we're going to let M be the mechanical checkup. Does that make sense? Letter-wise. Plus A be the appearance prep. Okay? So the expected value of the mechanical checkup plus the appearance prep is equal to just adding those means together. Okay? And so when it says the average, that's the expected value. Expected value is mean is average, right? So those all kind of go hand in hand. So that's, and it says total time spent. So that's 90 plus 60, 150 minutes. Standard deviation, we said yesterday, the standard deviation of M plus A is equal to the square root of sigma M squared plus sigma A squared. It's the variances that add, so I have to square the standard deviations to add them, and then I can take the square root to get back to standard deviation. And so that's going to be 15 squared plus 6 squared. It's 225 plus 36. Is 16.16 minutes. So on average, it takes them 150 minutes to do the appearance prep and the mechanical checkup with a standard deviation of 16.16 minutes. Now for 2, what are the mean and standard deviation for the total expense to prepare the car? So we need to convert from the time it takes, we need to convert our mean from the time it takes to the amount it costs them. So it's $50 an hour to do the mechanical checkup. So that's the expected value of 50 M. 50 times the time would give you how much it's going to cost them, right? But it's per hour, right? We're definitely not paying $4,500. 90 minutes is how many hours? 1.5 hours, right? So 90 minutes, yes, is 1.5 hours. And 60 minutes is 1 hour. So you have to make sure your units are right so that you can do the calculations correctly. So it's $50 times 1.5 hours. So that's 50 times the expected value of M, which is 50 times 1.5, which is $75. The expected value is $6 per hour on the appearance prep. That's 6 times the mean, which is 6 times 1, $6. So what is the total amount of money it costs for both procedures? $81. Right? So we're going to call this the expected value of MC plus AC, the cost of mechanical and appearance prep. Okay? But standard deviations also have to be converted from minutes to hours. 15 minutes is how many hours? Fourth of an hour, so 0.25, right? And 6 minutes is what percent? 1/10 of an hour, 0.1. Right? 60 divided by 60 is 0.1. 15 divided by 60 is 1/4, 0.25. So now my standard deviation for the mechanical cost is going to be $6 times 0.25. Is $1.5? No, wait, that's the wrong one. That's not mechanical. Mechanical is 50. I can multiply my standard deviation by a constant, so I'm just converting from dollars, from hours to dollars. 50 times 0.25 is 12.5. Standard deviation for the appearance cost is the 6 times 0.1, which is 0.60. Now, can I just add those for the standard deviation? I'm going to say no. Did we just add them up here? We couldn't just add these standard deviations for mechanical checkup and appearance prep. We had to use the Pythagorean theorem formula. So I have to do the same thing here. I can't just add my standard deviations. The standard deviations don't add, the variance adds. So that's the square root of 12.5 squared plus 0.6 squared. Which is 12.51. MC plus AC. So we expect it to cost an average of $81 to prep a car. Everything's like dying of battery. My calculator's dying. My Apple Pencil's dying. My iPad's dying. We expect it to cost $81 on average with a standard deviation of $12.51. Okay. What are the mean and standard deviation of the difference in the cost for the two phases of the operation? How is the mean and standard deviation different when we subtract? I want the expected value of mechanical checkup cost minus the appearance prep cost. That's subtracting the means. So that's 81. Wait, no, sorry. 75 minus 6, which is $69. And the standard deviation is the same. I still have to add my standard deviations because it's getting more variable. Even if I'm subtracting the two numbers and all the possibilities, I'm adding variability. So it gets more spread out. So it's still the 12.51. It's important to note that so you don't have to redo a calculation, right? The answer should be the same whether I added or subtracted for the standard deviation. Okay, and then what's the probability that it will take longer to do the appearance prep than the mechanical checkup? What's the probability that m minus a, the time it takes, if the appearance prep is longer, won't that subtraction be negative? If the second number a is bigger, that subtraction is less than 0. Not equal, just less than. So I have a mean and a standard deviation. And I want to know the probability that that difference is less than 0. Remember that the mean of the difference is 69 with a standard deviation. Oh no, wait. This was not the time, right? It's going to be the time subtracted. It was 90 minutes minus 60 minutes, right? Which is 30 minutes. And the standard deviation of m minus a is still going to be 15 squared plus 6 squared, which was 16.16. If I have a mean and a standard deviation, and I'm asked for the probability, what do I use? The normal model. If I have a mean and a standard deviation, and I'm asked for the probability, I should be using the normal model. My mean is at 30. My standard deviation is 16.6. I want to know the probability that this difference is less than 0. How do I use the normal model? What do I calculate? Anybody remember?
68.
Oh yeah, 68, 95, 99.7 rule, but we want something more accurate.
It's been a while, we
It may have. It's the only well, it's really not the only letter we've used, but there's a letter we used towards the end of the alphabet. My daughter's name starts with it. We use the z-score. My daughter's name is Zaylee.
Towards the end of the alphabet, it is the end of the alphabet.
I know, but I didn't want to give it away too much. So that would be, the z-score is 0 minus 30 divided by 16.16. So that's negative 30 divided by 16.16, and that's negative 1.856. Anybody remember how we get the probability from the z-score? No. It's a calculator command. That's our maximum. Normal CDF, because I want less than 0. The z-score at 0 is negative 1.856. So because I want less than, my lower bound is what? Negative 99. And my upper bound is negative 1.856. and plug that in. Second distribution. And we get 0.0317. So there's a 0.0317 chance that the appearance prep actually takes longer than the mechanical checkup. No, 3.12%. Yeah, 1, 2. 3.17%. So we're going to start bringing back information that we've needed before. The normal model, calculating the probabilities with normal CDF, and those are pretty much not going away until you take the AP exam. It is a part of everything we do from now on. So let's use the last 5 minutes for why variances add. Okay. Then all we have left in chapter 16 is looking at different AP problems. And this is a common concept on the AP exam. We have 2 piles of fruit. We have grapefruit. They range from 16 to 24 ounces. And the oranges weigh from 9 to 13 ounces. If you pick one at random, one of each at random, the sums could be as high as 37, right? And if I got the 2 largest, the highest the sums could be is 24 plus 13, which is 37. But if I got the 2 smallest, then my sum would be 25, which gives a range of 12 ounces. Now, it's not variance, but variance, range, and standard deviation are all measures of spread. So when I subtract the weights, the biggest difference in the weights is to take the biggest grapefruit minus the smallest orange, right? And if I subtract those, I get 15, 25 minus 9. And then the smallest difference would be to take the smallest grapefruit minus the largest orange. And if I subtract those, I get 3. My range is still 12. So even though I subtracted the values, my spread is the same, whether I added them together or subtracted them. Right? So because range and variance and are measures of spread, we can kind of use this example to illustrate why they're going to add and why they end up being the same, whether I add or subtract them, because that range stays the same. Okay. So that is that. Antibiotic A is known to effectively cure the infection 60% of the time. Treatment with antibiotic A costs $50. Antibiotic B is known to effectively cure the infection 90% of the time. Treatment with antibiotic B costs $80. Antibiotics, they work independently of each other. Both antibiotics can be safely administered to children. A health insurance company intends to recommend one of the following 2 plans for treatment of children with this ear infection. Plan 1, treat with antibiotic A first. If that doesn't work, then treat with antibiotic B. Plan 2, treat with antibiotic B first. If that's not effective, then treat with antibiotic A. Part A asks, if a teacher treats a child with an ear infection using Plan 1, what's the probability the child will be cured? And if the doctor treats the child with an ear infection using Plan 2, what's the probability the child will be cured? Okay, so first of all, we have to find the probabilities, and that's incorporating unit 14 or 15, depending on whether it's independent or not. Here it tells us the antibiotics are independent of each other. So you're looking at chapter 14, independent probabilities. So what has to happen? What happens first? Well, the first thing is the probability that we took A and it worked, right? That's plan 1. That's the first thing they do, right? They give the kid antibiotic A. If it worked, they're cured, right? Yeah. What about, what's next? What's the other option? that A did not work, so they give them B, right? Well, no, that's not given. Sorry. Back that up. It's a probability that A did not work, and then they give them B. Because it's not given because probability of B working doesn't depend on whether or not A did work or not. So it's just A did not work, and now we're going to give you B. Okay? What's the last probability? Right? That neither worked. Right? So my entire events, all of my outcomes include A worked, A didn't work, and B worked. And then the last outcome that A didn't work and neither did B. Okay? But we're asking for the probability that the child is cured. So these are the two possibilities, right? What's the probability that A worked? 0.6. Plus, what's the probability that A did not work? 0.4 times the probability that B did work. 0.9. So that's 0.6 plus 0.36, which is 0.96. So with Plan 1, there's a 96% chance that the child is cured of their ear infection. What's the probability that they are not cured of their ear infection? 4%, right? That comes into play later when we talk about the expected value and making the probability model. Okay? So given this information, can you calculate the probability that Plan 2 worked? Yes. So for the probability that Plan 2 works, that's the probability that B worked, plus the probability that B did not work and A did work, right? And so that's 0.9 plus 0.1 times 0.6, right? 0.1 is the probability that B did not work, and 0.6 is the probability that A did work, which is also 0.9 plus 0.06, 0.96. So if we're looking at two different treatment plans and the probability that the kid is cured is the same, what are we going to use to determine which one we're going to use to treat patients? Cost, right? It all comes down to cost in the end. So for B, compute the expected cost per child when Plan 1 is used for treatment. Okay, so here's Plan 1. So our medication, or it's the cost of the medication. So what happens first? They give A, right? How much does it cost? $50. What's the probability that it works? 0.6. The probability that if I gave you A for $50 and it worked is 0.6, right? And so there's a 60% chance that they only have to pay $50. Okay, now what's next? If they already paid for A and now they have to pay for B, what's the cost of that? $130, right? And the probability of it costing $130 is 0.4. Because whether or not you're cured with A, they still are paying for you to do B. And whether or not you're cured with B, it's still costing them $130. If I want to break it up, I could say 130 and 0.36 and 130.04. This is the probability you're cured, and this is you're still not cured. Think about the situation. I've already paid for you to take antibiotic A. there was a 60% chance that it worked. That means there's a 40% chance you're going to have to take both A and B, right? Whether it works or not, they're still paying for you to take both medications. So it's still costing $130, whether you're cured by B or not. Because those are the two possibilities, and remember, this has to add to 1. So I could separate it into costs $130 if you're cured, but it still cost them $130 if you were not cured. And that adds up to the 0.4. Yes? How do I find my expected value? Right. 50 times 0.6 plus 130 times 0.4. We get 30 plus 82, 112. Wait, no, that's not right. I have a wrong key in here. 52. $130 times 0.4 is 52. I accidentally hit the plus sign. So the total expected cost for plan A, or plan 1, sorry, is $82. Can we do the same thing for plan 2? Okay, can you do it? I'm going to give you a chance. Mm-hmm. Okay, so what does our probability model look like? What's the first cost? $80. And what's the probability that they only have to pay $80? 0.9. And then what's the second possible cost? And what's the probability they pay a total of 130? 0.1. So 80 times 0.9 plus 130 times 0.1. So 72 plus 13, right? 85? So then the last question is, based on the results in part A and B, which plan would you recommend and explain why? Remember, you are working for the insurance company. You are not the parent.
Oh, so we want to save money.
We want to save money. We're the insurance company. Plan 1, right? We would choose plan 1 because the probability of ultimate cure is the same as plan 2, but on average, it's going to cost us $3 less per patient. And if we have thousands of patients across the United States that get ear infections, we're saving a lot of money by saving that $3 per person.
Plus, we would say plan 1 is more cost efficient.
Yeah, will you explain more? Like, you want to say plan 1 because the probability of a cure is the same, but plan 1 costs less per person on average. Now you want to try to use statistical language. Average is $3 less. The probability of a cure is the same. So as the insurance company, the end result, we don't have to worry about, well, we're going to save money, but they're less likely to be cured. As a parent, I'd rather have the more expensive treatment first, right? Because then I'm likely to not have to give my kid another antibiotic for another 10 days, right? Or however long.